Okay, guys. Before we move to the next talk, on behalf of the organization team, I would like to give a big thanks to the people at Principia Institute in the name of Wellington. Wellington is right there. He's not the only one in Principia Institute who's been helpful through these days, but thank you very much. And also, yeah, big Homer applause. And also for the ICTP-SAIFR staff, you have Tiago over there, you have William over there, but you also have Humberto who sent you many emails, and Lisa also that has sent you many emails, and they are doing all the hard job. So thank you very much, guys. And thank you all the participants, of course. Without you, there won't be any workshop. So, oh, thanks. Whoa, let's rock and roll.
That's nice.
Yeah, back to science now, guys. Pleasure to introduce you Professor Alessandro Codello, which is almost from here, right?
From here, yes.
Almost from here. He's from Uruguay. I mean, he's Italian, but he's
I'm in Uruguay at the moment, yes.
Yes.
So,
so he's going to talk about a lot of cool stuff, again, asymptotic safety and about effective field theory as well. So please, Alessandro, whenever you're ready, and thank you.
So thank you very much for the organizer to invite me, and it has been a very nice workshop for me, seeing a lot of attempts to prove quantum gravity in the lab. It's something that I really appreciate. So my talk is somehow a continuation of the one of Antonio's, but I also give you some of description of some of my work and my personal evolution, if you want, inside the subject from the early beginning to try to then make connection with the effective theory of quantum gravity, and so with what John was telling us. So in this first part, I just want to make a review, because in any case, this is a very general audience. So I will try to make it a little bit that doesn't completely overlap with what we just heard. So I will be more a little bit from the point of view of RG theory, universality, and what a fixed point means, and what is really a theory. So we live in the paradigm of the RG theory, where basically we have a theory space, which is a concept where every possible theories which is consistent with the symmetries can live. It's an abstract object. But what is really important is that the theory space, once we define a theory space, and the proper way to do the coarse graining, which is a very interesting subject that goes through the whole subject of science. So somehow the RG is a unified theory that can be used to describe probability, transition to chaos, phase transition in equilibrium, out of equilibrium, and even, and this is the great achievement of Wilson, it unifies the infrared and UV. So it can be used as a kind of theory of what is a functional integral. Because nowadays, as it was described before, we understand that in principle, to make the continuum limit of a functional integral, we need some specific conditions and things happening in the ultraviolet. So what is really important is that once we define the degrees of freedom and the symmetries, the theory space and the RG transformation give us some fixed points. These are specific theories that emerge. We don't write their Lagrangian. Their Lagrangian are a prediction. And they are key for a lot of phenomena and a lot of ability to make prediction. And in particular, in a unified framework, we know that fixed points describe continuous phase transition. Most of the time, they can be solved exactly. They are needed as continuum limits. And in a lot of situations, they are conformal field theories. Okay? So the main goal of the RG theory, once we define a theory space, is to find these fixed points. And the second predictive ability that we have is that the RG flow, which is generally and naturally non-linear, can be linearized around the fixed point. And there's a region, which is the scaling region around that, that is characterized by physical quantities that scale according to some universal numbers, which are really fundamental constants of nature. Okay, the critical exponents of the Ising model, it's like pi. Something really deeply rooted in mathematics of reality, okay? And so we have this region around the fixed point where we have the possibility to calculate universal quantities in general. Critical exponent, universal scaling ratio, scaling functions, and so on. And we have the fundamental distinction between relevant and irrelevant, which is a local concept that applies in the vicinity of a fixed point. If you come from CFT, you know that this is the quantities, this number are exactly the numbers that allow you to define exactly what is a conformal field theory. So these fixed points are somehow some lighthouses, you know, or when you play these video games where you have to explore and some kind of environment that it's all dark, you have the fixed point is where you start, and then you start to shed light around those. So once you have the fixed point in the scaling region, you can start thinking of starting your flow from there, terminating your flow from there, or trying a way to construct a trajectory that connects to different fixed points. So here we need a new kind of mathematical framework, and basically we have three major types of mathematical frameworks that can be used to do that. So we have things like the C theorem in 2 dimensions, which is like an exact theorem that tells us some general properties of the flow, that the central charge will decrease or along the flow. We have other things which are very popular, are called local RG and Weil consistency condition that can be very important. Or we have the subject of exact flows. So the ability to write down in a formally exact way the RG transformation that live on this theory space, okay? And this is the kind of tool that has already been introduced and is the kind of tool that today I will use. But I want to say that this is just a tool, as it was said before, you know, to discover universal properties on one side and the existence of this fixed point. So then we have the types of flows. So one lesson that somebody has to have firmly written in the mind is that a theory is a trajectory in theory space. And we can have very different types of theories. So we can have theories which we can call fundamental, like an asymptotically free theory like QCD. It's a theory that starts at a fixed point in the ultraviolet and goes all the way down to the border, which means a massive infrared, okay? Otherwise, we can have other kind of theories, like the Ising model on a lattice. So it starts at a finite point, so there is a scale here, lattice spacing, and then we can, this will evolve, and most of the cases it will evolve to a kind of massive infrared, but there are some specific way to tune some of the parameters in such a way that your infrared is controlled by a fixed point. So these are the two uses, the unification of infrared and UV made by the RG theory. This is the case which is used to make prediction asymptotically far away for high energy. You know, quarks behave like free particles. It's a good approximation. So we can make approximation at asymptotically away from where we are, you know, because we know that there are two main principles that allow us to make predictions: universality and effectivity. Universality, when you have a fixed point, you can take asymptotically far away prediction. When you use effectivity, is when if you're in a point in the space, you can make a lot of steps if you're bounded by an error that you decide, okay? Because in any step, I only need to add definitely many operators. But if I want to go very far away, or if I want to come from very high away, okay, from the UV, then I need either a fixed point in the UV, and then I have a fundamental theory, or I have a fixed point in the infrared. Then clearly I can have a theory which is just an effective theory, okay, where we have a point where we start that has a cutoff, and we finish in some infrared, okay? And then clearly we have some very special kind of trajectory that can connect to different type of fixed points. And also remark that a fixed point can be both UV and infrared. I don't know, in 2 dimensions, the fixed point that corresponds to the Ising model, it is infrared for some direction, but it is also the asymptotically safe, in this case, fixed point, if I see it from the degrees of freedom of a scalar for a free Majorana, or it's a Gaussian fixed point for asymptotical freedom. So it's a complex situation that you need to understand, okay? And this is the paradigm in which we work. And most of our work, by applying non-perturbative RG of various sorts, is to try to construct this theory space the best that we can. Okay, now I come to the work that I did mostly during my PhD, master, and first postdocs, in where I work with Roberto Percacci and with Martin Reuter. They were my master thesis advisor and my PhD advisor. And during this time, it was really the beginning of the asymptotic safety. And we had the first works of Martin and then also with Frank, and we have to remember Wataru Soma. That was the first one to point out that the fixed point that was found by Reuter in the first paper was actually something that could be used for asymptotic safety. And so when I entered, we had the fixed point, but we didn't know yet if the critical surface was finite dimensional. And this is exactly the key point. And in fact, this is what Weinberg wrote us after we made a paper about asymptotic safety in R-square gravity. Because also when you include R-square gravity with the Weil term, you're still basically, you're still not proving that the UV critical surface is finite dimensional. So our goal was to find a way, and there are a lot of technical challenges in this, is exactly the technical challenge that was discussed before, how to include operator and make this kind of calculation. But before showing that, let me just review quite rapidly, because we already had an introduction to the subject, what is asymptotic safety and what is the technique that we use. So the idea is that, and what is you have to take home is that even if gravity is not renormalizable in a non-perturbative way, even if gravity doesn't have an ultraviolet fixed point that makes it renormalizable in a non-perturbative way, still we have a theory space for gravity and we have a flow for gravity. Because the fundamental idea of RG is that it is difficult to make sense of the path integral. But when I take the difference of two path integral, I have only one shell. I have only one integral to do, one functional trace. So I can define locally the flow, and then I can study the flow where it goes, okay? So I start in a well-defined problem, in principle, okay? And actually, the caveat is that even to do this, there are some problems. And the problems are related with the fact that this is true when you don't have gauge symmetry. When you have gravity or gauge symmetries, the implementation of a cutoff starts to be a little bit tricky, because the cutoff is something that compares length scales, but length scales are taken with respect to a metric. So when I decide to divide between fast and slow mode, how can I do that? I need to introduce an additional structure, which is an arbitrary background, and I will carry this arbitrary background all the way of the calculation. And at one point, I will be forced either to enlarge the theory space, okay, allowing the breaking of the fundamental symmetry, or I will have to close the theory space in such a way that I preserve the symmetry, okay? But this is a general problem. It's a general problem on, why is this? Okay, this is like, maybe, okay, so these are all technical things, and if I have some time, I will discuss some of them. So what we did in these two papers was to demonstrate that within certain number of footnotes, and then I will tell you exactly which are these footnotes, actually in the theory space defined by Martin Reuter with the flow equation defined by Martin Reuter and Christoph Wetterich, actually truncation of general relativity actually have a fixed point with a finite dimensional UV critical surface. And I already tell you which are the caveats, the assumption that we made. So first of all, we are working in the Euclidean like the whole subject. Let's put this on our hand. The second one was that we proved that for a family of operators, only for the Ricci scalar curvature, with the plan that this could be solved. And actually in the later year there was a lot of papers and that came and actually solved that, basically, because we are now able to include systematically a lot of operators. And actually the results in the work that was done by Daniel Littim, Kevin Falls, in which they introduced as many as 70 operators. So there is a remarkable stability in that sense. Then we have another kind of problem which is more related to the fact that I just mentioned, the background independence of our calculation. All the calculations that I did were conditional to a certain way to close the flow, okay? And actually one of the main things that we're doing together today is to go beyond these kind of closures. Another thing I want to say is that we normally have let's say, 3 different kind of application of the RG. Because there is the RG related only to the fixed point, which is the one devoted to the computation of the critical exponents. And that one can be done basically with any kind of regulators, because we have the fundamental theorem of the RG that we can change in theory space the type of coupling, the parameterization, but the spectrum is CFT data that we can compute, and we normally could compute it in many different type of way. In my application, in my studies of statistical mechanical system, I always use the functional RG, but I always double check my result also with other approaches, because this is the only way to be sure. We are computing universal quantities. Another thing is that was discussed before is the running of the coupling. Because the running of the coupling, it's true, it's physical, because nature is inherently fractal. So when we look at the charge of an electron, we know that at quantum mechanical level, a Gaussian sphere, the result that comes out, because the object you have inside is not a classical object, depends on the radius. And so this tells you that you see different values for the charge depending on your resolution. This, in the quantum field theory framework, is normally reflected in the presence of a momentum dependence in the effective action. And most people in the audience know this topic very well. Another thing is the running with respect to the parameters of the RG. And so for this kind of application, one has to consider this difference. What we normally do in the asymptotic safety and with the effective average action is to use the fixed point with a finite dimensional critical surface to define our functional integral, and then we flow down to k equals 0, so we integrate out, and we recover the full physics. But by doing in this way, if the theory is UV finite, UV has a finite dimensional critical surface, the action I get in the infrared will depend only on a finite number of constants. Okay? And so if I find a way to measure those, I have an ability to make an infinite number of predictions. This is the way in which I've always operated inside the asymptotic safety. Okay, in any case, our result here was also welcomed by Steve, and actually in this paper where effective field theory past and future, we are probably not paying the copyright, so it has been deleted, but in any case, these were actually our results that were showing that in our kind of approximation, in our works that I just said, gravity actually seemed to be asymptotically safe. And most of the research that came later on was to make this result more and more sound, okay? So this was one of the results. The other thing that came after this was, okay, now let's try to eliminate all the footnotes, okay? So adding more operators, adding operators that have all the tensor structure of gravity, and this is something that has been more under control. Adding and studying gauge invariance, pariparameterization invariance, this also has been done. But one of the main problems is that was still that when we do the coarse graining procedure, we necessarily break either gauge or space-time symmetry. So normally, when you want to preserve gauge symmetry, but you break space-time symmetry, you're basically doing lattice gauge theory or dynamical triangulation or causal dynamical triangulation or matrix models. It's one of the branches. In the other branch, we decide to retain space-time symmetry, but we break gauge symmetry. Okay, so we do effective average action with modified Ward identities, which are poisoned by the cutoff term, or we use, for example, the background effective average action method, which maintains covariance, but at the cost of having 2 metrics, okay? And in particular, now I have some technical slide that I will just go more faster because there are a lot of details. It's a very nice subject, but the point is that after you implement the cutoff, and one of the beautiful things of implementing the cutoff a la Wetterich and Reuter is that you can work consistently on a curved background. You then use the background metric to say which are the fast mode and the slow mode, because you have the Laplacian on the background to do that, okay? So it's basically you bootstrap. Took an arbitrary background, used that background to say what is fast and what is wrong, okay, and then I will have an object that will depend on both of them. And then at the end, I need a way to close the problem. So at the end, we normally get a flow equation like this in gravity, and this will depend on a multiplet of fields, so there will be the ghost and h mu nu, which is the gravitational fluctuation, but also on a residual background, which I use to construct the cutoff. And then I can project that on the gauge covariant part, okay, which is the one where I put to 0 this multiplet of fields. And now this is the gauge effective average action that has been used in all this original part of the studies for almost 10 years. We have been using only this kind of approximation. But this is not closed. So this means that either I enlarge my theory, what I need to do is to enlarge theory space, okay, and have not only, let me call it the more physical couplings, but even some terms that can parameterize the breaking of the symmetry due to the cutoff, or if I want to preserve covariance, the fact that I have two metrics, okay? And in particular, this is the original truncation made by Reuter, where we have the running Newton constant and the running lambda, and they scale with their dimension in the usual way. And then, okay, you do the calculation, and after you do the calculation, you end up with a set of beta functions. One of the nice things of the non-perturbative RG is that your beta functions are valid in any dimension, okay? But when you do this first calculation, you are left with the anomalous dimension of the fluctuation multiplet, okay, which is this thing made in red. And this is the state of the calculation. So normally, one adopts the one-loop approximation, okay, which is the one in which you just put them to 0, or the standard approximation, which is the one that has been used in all the first papers. And this is a way to close the system. And actually, this is a very nice way because you can show, for example, that if you apply this to gauge theory, you get, and you apply to n equal 1 supersymmetry, you actually recover the Novikon-Schiffmann-Weinstein beta function, which is an all-order result, by exactly this kind of resummation. What I did together with my students at that time was, no, we have to go beyond. We have to live in this enlarged theory space. And so we have to find another way to compute these anomalous dimensions. And you can do that. The calculation is relatively difficult, and you get some result. And when you do that, you find the fixed point. And in particular, to my personal point of view, it solves a critical problem that we had at the beginning, because in the picture that you see this surfing wave, no? And you have a fixed point that has a spiral. When you have this fixed point has a spiral because it has a complex conjugate pair of eigenvalues. So this is not something that you normally find in a quantum field theory, and there has been a lot of discussion if this was a problem or not. What was very nice was that once you do a more non-perturbative closure that allows you to consider this enlarged theory space somehow to give to the flow the possibility to breathe in this game between the two metrics, okay, then you solve this problem. And you find actually a fixed point that has completely real eigenvalues. And this is very nice, because at this point we have solved one problem, and then this can be applied to a whole tower of different operators. So we have a framework, or you call it a toy model of gravity, or something that, where in principle you have an ultraviolet fixed point. So now the next question is, okay, but this is the this is the UV, okay, and this is the infrared. So what I need to do is to flow down from this fixed point and go to the infrared, compute my effective action, okay? Effective action that will depend only on the number of relevant parameters in the ultraviolet. But this is a non-perturbative fixed point. So how can we do that? So we need to find a way to do that. And the proposal that we made here was, okay, we know that the effective action in the infrared is a non-local object, or a quasi-non-local object. It's something that will build up a non-trivial structure in momenta, because the effective action is the 1pi generator of my diagrams and so on. So it means that I cannot, if I am interested in the infrared physics, so in the full physics, I cannot only look at the local operators that were a right choice if I was looking only for the UV questions. Once I solve the UV, now I need to take that information and integrate that information down to the infrared. And this is exactly what we did in some papers, first in 2 dimensions and then in 4 dimensions, where we started to make a curvature expansion of the effective action. And then the flow equation now will be converted in beta function for the coupling and functional equation for these non-local structure functions that will evolve from 0 or from the value they have at the fixed point all the way down to the infrared, okay? And actually, you can do this, and it's also a nice part of mathematics, especially in 2D where you can solve the model and discuss a lot of details, which we don't have time. But when you apply this to 4D, we make finally the connection with the infrared. And since in this picture that I show you, in this first calculation, we were only looking at the terms up to quadratic order in the curvature expansion, the terms that we were getting in the far infrared were independent on the initial condition of the fixed point, because we recovered exactly the covariant version of those terms which are responsible for effects like the correction to the Newtonian potential that was explained to you by John Donoghue. And in fact, this is the key lesson that we have to bring home, is that let's even assume that all the other caveats that I said can be solved, that this translates to, we can really complete our calculation respecting gauge symmetry all the way by including all the necessary adjustments. We can put inside all families of operators. We can translate these things to the Lorentzian framework, and then we flow down and we have an action that we should use to do quantum gravity. The point is that any signature of the fixed point will start to appear in the cubic terms, not before. Because it's only from cubic terms that they start to be basically constrained. They are the first parameter that are a prediction, okay? And so, what is the problem here? The problem is that these are next to leading order corrections. And already the leading order correction that should be reproduced and are reproduced, okay? Because any theory of quantum gravity, would it be string theory, loop quantum gravity, asymptotic safety, have to flow down to the same action, okay? And so the problem is that we have R squared terms. So the problem is that in principle we can do it, but if we just want to do phenomenology and really take home the universal results of quantum gravity, we first have a whole generation to devote to the effective theory of gravity. And actually, it's nice because by doing all this calculation, we learn a lot of techniques to do calculation covariantly, okay? So it means that if you really think that asymptotic safety exists, first stop a moment, and for a couple of years at least, you should do all the things that you can do in the effective theory of gravity. And it's from those things that you should extract the possible ideas for experiments. Because if you don't see the things that the effective theory of gravity you see, it's very difficult that you can see an imprint of a different UV completion. So this is exactly what John said. The effective theory of gravity is renormalizable in the effective theory sense. It makes sense. There is no contrast between quantum mechanics and GR, but the theory is not complete. I offer a completion, but the completion gives you next to leading order terms. So this is my takeaway lesson for the more phenomenological audience, okay? And so then we are here to remember that we have two fundamental ways to make prediction in theory: effectivity and universality, okay? One, it's used needs fixed point, and the other one, since it makes a finite trajectory in theory space, it only needs the symmetry. And by each iteration, you just need to add more information. So you keep yourself in track by matching or measurements, okay? And so we are here, and it was nice, something else that I did, because it was basically the same kind of mathematics, and we had a lot of tools, okay? And so when we do an effective theory of gravity, we do something that I was already explained, but what I wanted just to give you the taste for is that these are the terms that we use, for example, to make all the leading order calculation, and they will need renormalization from the second tower. And up to here, the fixed point will tell you nothing. Is when you do the next iteration that these objects will be fixed. These coefficients will be fixed will be function of these other coefficients in a way that depends on the fixed point. Okay? But since we will basically never look for a lot of time to this line when we do effective theory, we are just going back to the problem that we should just look at the effective theory of gravity. So then the only thing that I can comment more than what John did is that since we do everything covariantly, we are computing an effective action, which is a very nice object. Once you compute it, in principle, you just do the physics with that. So you can either reproduce calculation like the one of the correction to Newtonian potential and flat space. In principle, you can apply it also to other kind of backgrounds. So it would be very nice to see, for example, if in a tabletop experiment, those terms which are responsible for the Newtonian correction, when you apply them in other kind of configuration, can give rise to something interesting. Otherwise, here there is, these are all the universal predictions. Okay. Otherwise, we can add matter, obviously. Otherwise, you go to the level where you will study the correction and the possible effect of these non-local terms that you get in the effective action on, for example, in cosmology. We'll comment on this. So, how do you connect to the work of John or the work that you do in flat space? So when you do the computation in curved space, you do a curvature expansion. So your gamma can be expanded in a curvature expansion, and now this is only the part of the expansion that relates to pure gravity. And in particular, all the coefficients up here, these couplings, are free parameter in the effective theory, and they are also free parameters in the asymptotic safety. But then the form of these functions in the UV, in the far infrared, they are completely fixed and basically depend only on degrees of freedom, okay? So the idea of the effective theory is to compute this, couple this to all type of matter, and then look at the consequence, okay? So you can study all the kind of phenomena. And in particular, since gamma is the 1-pi generator, from the information of these structure functions that we can compute with nice mathematics related to non-locality kernel and things like this, or zeta function regularization is also another way to do that. We can add matter, clearly, and we can use it as the building blocks for computing, for example, the Newtonian potential. And clearly, also here there are a lot of details that we don't have time here, but you know that we get this result here, where basically we are coarse graining, and in place of having the mediation of a quantum graviton, we have just a point interaction with the correction. Now, in the recent year, in the last, let's say, 10 years, let's say, actually, this framework has become even more interesting for another reason, not much for the quantum part, but for the fact that the functional integral actually also spits out classical corrections. So nowadays, the whole formalism that I showed to you can also be used to study the two-body problem in GR, okay? And one can use Feynman rules, one can use all the techniques that have been used up to now, dimensional regularization, and all these kind of things to compute the effective action that comes out exactly like we did with having in mind the H-bar correction, but there are even the H0 correction, which are the classical one. So we can use all this framework to compute an effective action, and this will be the effective action between two masses, which will contain all the conservative and radiative information that you need to study the merger of two black holes or two very dense stars, and in particular that it's now used to compute the waveform. Okay, and this is actually for me was like a revival. It made me go back to all this approach, because now you have a formalism where in one line of the expansion is the classical problem, highly nonlinear, very difficult to solve, but that we have direct evidence. And then the next line, the H-bar line, is universal. It will be the prediction of every theory of quantum gravity that has a lot of information that can be dealt with. And then, in principle, there is the next row where finally the information of the fixed point will come in. Okay? And so, as you know, the problem or the fact of reality, the hard reality, is that general relativity, the quantum gravity, as an effective theory of gravity, is such a good theory that the correction it predicts are so small. And so they are so small that we say nowadays we have to invent other theories to say that we can falsify something. Because the hard reality is that they are here. These are the numbers, but they are small. So maybe another place to look, or this is what I came here for, because I was interested to know if any kind of quantum effect, entanglement, or any kind of super enhancement can be found in some specific situation where maybe this kind of terms, maybe not directly the one of the potential, but other one that belong to the effective theory of gravity, maybe can be extracted. And this is maybe something that you should look at. Otherwise, the leading order correction, maybe we should look at them in the universe. And so when we look at this thing in the universe, we obviously stumbled in the fact that we have Einstein's theory, okay, R, and then we have on one side, let's say, more in the infrared lambda, okay, and then we have on the other side more in the UV R square. And now we know, or we are forced to think, that both of these are more important apart Einstein, because we need lambda for the dark energy, and we need R square for inflation. And more R square starts to become the possible real candidate for inflation. And in fact, another thing that you discover from, if you think that GR is an effective theory, these terms must be there, and quantum mechanics wants them, okay? And in particular, the nice thing is that these two terms show us another phase of gravity, a phase where gravity is repulsive. We can have gravitational acceleration. That's the reason why the universe expands in inflation and then in the dark energy. And so, with some collaborators, in particular with Rajiv, we worked out a lot of toy models that were inspired directly from the effective action in quantum gravity, and not just phenomenological models. And when you do that, you discover a lot of cosmology, which is really nice. For example, a very simple model like this one, which is inspired by the effective action in quantum gravity, really shows you that you can have inflation driven by the R square term, and then when this term and this term start to be of the same size, you start having some very important oscillation, which is somehow a reheating, something that makes heat, which is, if you want, the Big Bang, and then you come out exactly in radiation. And then if you want, you can have dark energy at the end, like pure lambda, or even by some kind of non-local terms, which are present in the expansion, nonetheless. And in particular, it's very nice because really this is Starobinsky gravity, as you should solve it after you just do what we said today. Because the effective action of gravity for a space-time that doesn't have a Weyl tensor because it's homogeneous enough, it is really governed by this set of equations. And if you sit down and solve this equation without changing frame, but really like they are, like Starobinsky actually originally did, you find a lot of interesting phenomenology, which is very interesting. And so in this side, you can also you can really make, let's say, interesting phenomenological models, and you can go on and for example, look at this one. This is really the minimal case where you have the three, let's say, natures of gravity. The deeply infrared one, the deeply UV one, and the one of our scales, let's say. And in this case, you really go from inflation to dark energy. But you can also make more, phenomenologically correct models by including matter and radiation, okay? And so, for example, another direction is that one that we didn't discuss here. I discussed only expansion that were analytic in the curvature, but non-local in the momenta. At the same time, you can think that in some configuration, if the space is homogeneous enough, actually the effective action, the trace log, will give you terms which are non-analytic in R, for example, or in the geometric objects, okay? And for example, the effective theory of gravity will give you corrections to the R square. So we have correction where you have an f of R multiplying R square, okay? And now this is almost 10 years old, and now this exclusion regions outside of this region is excluded, or actually becoming more and more smaller, and we're going more and more in the direction of having Starobinsky or just a small quantum correction to the Starobinsky model. So the idea that gravity has inside enough space to really make falsifiable prediction and interesting prediction for gravity at the lab scale or at the cosmological scale is completely there. And okay, that's what I wanted to speak. I finished a little bit early because we're at the end of the day, and I skipped a little bit of technical slides that I think it was too
Oh.
complicated.
Thanks, Alessandro, for the cool talk. So questions, guys?
It's just a naive question. So you have shown that, I mean, somehow you computed gamma k and integrated down to k
Yes.
equals to 0, and you get the same results as John for the correction of the Newtonian potential.
Yes.
But of course, I mean, the gamma k was computed in a Euclidean setting, while John, as far as I know, did the calculation using a Lorentzian setting. So can you comment on that?
Yes, in this case, the numbers are the same, I will say. Exactly like when I do my calculation in electrodynamics, and I use these techniques to compute, I don't know, alpha over 2 pi of a Schwinger anomalous dipole moment. The calculation with the heat kernel, which is what we do, is basically, it gives the same result.
So the
But you know, when then we apply this to cosmology, we do the weak rotation, and we have to impose the right causality in the propagators and all these kind of formal things.
Okay.
And there are a whole subject about how to do that. In particular, this is what we did when we did the cosmological models. I didn't say that the cosmological model or a version that weak rotate back this to, so we do this. Clearly, the assumption is that this is something that we can do or try to do.
Yeah, you just spoiled my
Or
second
at least
question. Yeah.
not so naive that it justifies trying to do it to see what comes out.
Okay.
There is a
thank you.
question from.
Actually, I just wanted to comment on the same thing, because just to make sure I understand what you did in there, what I saw you doing is finding the non-local log box terms, or R log box, which is different from the running of the local terms. And you and Roberto are people that have shown how you get these non-local pieces also as you approach k is equal to 0. And so what you have reproduced in that particular piece there is the vacuum polarization
Yes.
diagram, portion of the calculation. But it's not from the local terms, it's from the non-local log box terms, which most of the time don't show up in the FRG. They just show up as you approach k is equal to 0.
So
Is that
the question is if the non-local terms came out only when k is equal to 0.
Right.
And in fact, I have this case here for the two-dimensional model where I can do the calculation completely because the theory is free. You see that this is the gamma k effective action at curvature square, and you get something that is non-local. And in k equals 0, I recover the non-locality. But it's only in the last moment that I recover the non-locality. You see, because here it doesn't go to infinity. So it's a non-homogeneous convergence.
Right, that's what I was trying to bring out, is it's that last k is equal to 0 where you find these, and it's distinct from the rest of the running.
Yes. And in any case, here the running is a mathematical way to transform an integral in a differential equation. So once you go down to k equals 0, it's just a way I had to evaluate the path integral. And the only thing is that if my starting point depends on a finite number of parameters, then my final result will only depend. So I have an algorithm that by fixing 3 numbers, by experiment, I predict infinitely many, and then you can test in a lab. Other thing is the spectrum at the fixed point. Other thing is the physical running of the coupling that sometimes applies and sometimes it does not. So this has always been my understandings. Exactly from, you see, this is 2010. So I always try to say we should do like this. And this is just 1 year after, I think. So yeah, it's the same year. And then in another paper, we added the matter part with Les Laved, with Tonero, and to complete the calculation. There is a question up there.
Can you make a quick one? Yes, before. Thanks, Nicholas.
I noticed that when you were writing the derivative expansion, you kept the Riemann square term, but you didn't add, for example, the total derivative of the Ricci scalar. And the Riemann square term can be rewritten in terms of the Gauss-Bonnet term, which is a complete derivative in 4 dimensions. So I would like to know whether the Gauss-Bonnet term plays a relevant role in your
So
calculations.
if you're in strictly in 4-dimension, there are two objects, two independent operators that you can reshuffle by the, and so here I choose R and R mu nu, and something similar applies for the form factors, because you can always reduce the eliminate one form factor by pushing information in the 3 curvature terms. So at the level of 2 points, you have only two objects. And this comes even if you just try to invert the propagator of gravity and flat space, you have basically only two independent objects. Okay? So you can if you want to study things outside of 4-dimension, then you have 3 objects with 2 curvature, and one is the Gauss-Bonnet, if you want. Then clearly, if you work with the space-time, with the boundary or other condition, you should worry, and there is a work about from Martin Reuter that he includes the boundary terms and this dialogue with all the kind of terms. While another question is if you do dimensional regularization, should you keep or not this term? And there are some work, for example, by Shapiro and Peixoto on these kind of things. But yeah, in general, you have, outside of 4, you have 3. In 2, you have 2. In 4, you have 2 objects.
I see. Thank you.
So let's thank the speaker again.
Thank you.